Welcome back, everybody. This is our video solution to problem 17 from the Fall 2020 Math 210 final. Here we are back to solving differential equations. This time we are going to do it using power series. So this is certainly not the easiest way to solve this particular differential equation. It's more of a proof of concept. But what we're going to do is assume that this function y has a power series expansion. So we'll write this generic power series expansion, and then we're going to put it into this differential equation. And by Fuchs' theorem, we actually know that this is going to work, and we're going to have a radius of convergence equal to infinity, right? So this method will work by Fuchs' theorem for this particular differential equation and have radius of convergence equal to infinity. Great. All right, well, let's put y into this differential equation. So we have 0 equals y double prime plus 2y. So if I take the second derivative of this power series, well, the constant and linear term will die, so I can start at 2. And let's see, when I take a general term, the n comes down, so I get n a sub n x to the, oh wait, we're going to do two derivatives. So actually, I got to do two things to pull down. First, I pull down an n, but then an n minus 1. And then I'll be at x to the n minus 2. So this is equal to y double prime. Now let's write down twice y. Well, that's easy. I just multiply this power series by 2. So I start at 0, and now I have 2 times an x to the n. Okay, so this is my 2 times y. I'd like to re-index this because I want to combine these, and I need these x's to have the same power. So we're going to re-index. When I re-index, my n's are going to go up by 2. So I'll have n plus 2 times n plus 1, a sub n plus 2, x to the n. But when I go up by 2 with my n's here, in the index, I have to go down by 2. So now I'll start at 0. And of course, I still have here this sum starting at 0, 2an x to the n. And I'm really happy because now, in addition to having the same powers on x, I also have the same index. So I don't have to peel any pieces out here, right, to make sure these start at the same place. Okay, so now I can put these together then. Starting at 0, how many x to the n's do I have? I have n plus 2 times n plus 1 times an plus 2, as well as 2an x to the n's. Now, on the left-hand side, I just had 0, which is its own power series, right? It's a power series where all the coefficients are 0. And we have a theorem that tells us that when we have two power series that are equal, their coefficients must be equal. The coefficients on the right are these monstrosities. The coefficients on the left are all 0. And so we conclude by our uniqueness theorem that all of these monstrosities, n plus 2, n plus 1, an plus 2 plus 2an, equal 0 for all n at least 0. Now I can solve this for an plus 2 and get a recurrence relation. So this implies that an plus 2 equals negative 2 over n plus 2 times n plus 1, and then times a sub n. Okay, again, this is for all n at least 0. All right, so now I want to use this recurrence relation to try to write down a formula for a sub n. So one thing I noticed right from the beginning is that these indices differ by 2, which really means I'm going to have two cases to deal with. All right, so I start with a sub 0. And I don't know anything about a sub 0 because this formula only tells me what to do when I start. Well, let's see, if n is 0, I get a sub 2. So the same thing with a sub 1. Like, I have no way to rewrite that. Fine, let's go to a sub 3, or 2 rather, right? That's the next one after a sub 1. Now a sub 2, I can rewrite using this recurrence relation. It's going to be negative 2 over, okay, now you'll notice the n plus 2's here match. So this is, I just take this number here, right? So I take a 2, and then this is 1 less. N plus 1 is 1 less than n plus 2, so n plus 1 is 1. And then I have a sub, okay, 2 less, so that'd be a sub 0. Now, one is probably tempted at this juncture to cancel, right? That's such an easy thing to do. But man, you got to just overcome what they've taught you all these years. So often in math, canceling just hides what you're trying to find, doesn't help you actually find it. All right, instead of going right to A3, let's stick with these even terms here. Let's go right to A4. So this would be negative 2 over, again, I just copy the index, so 4, then 1 less is 3, times A sub 2. Okay, but A sub 2 we have on the previous line. So I can rewrite this as negative 2 over 4 times 3 times, okay, my A2 is negative 2 over 2 times 1 A naught. And here I can put these together now, and I say, look, the negatives go away. I have two 2's. And again, I could write this as 2 times 2 equals 4. I'm not going to. I don't want to hide what's really going on. I'm multiplying by another 2. I'm just going to keep track of it that I have two 2's. And what about on the bottom? I have 4 times 3 times 2 times 1. Again, could multiply it out. Not going to, though. I'm going to just note that this is a product of all the numbers from 1 to 4, conveniently written as 4 factorial. And then, of course, I still have my A naught. All right, let's write one more term down. My A sub 6, I do negative 2 over, I copy the 6, I write 1 less, so 6 times 5, and then I have A4. A4 we have up above. So this is negative 2 over 6 times 5 times 2 squared over 4 factorial A naught. Okay, the negative is going to live this time. And now instead of two 2's, I have three 2's. I have 6 times 5 times 4 factorial. That's just the same as 6 factorial A naught. All right, I think I'm starting to see a pattern here. I have a sign which is alternating. I have a bunch of 2's. How many? Well, this 4 was 2 times 2. This 6 is 2 times 3. And look, whatever this times 2 part is, right, that's what's going in the exponent. And then in the bottom, I always have a factorial, and it matches exactly this number. And then I multiply by A naught. So I'm going to make a claim. I claim that A sub 2n, right, these are all evens in this column, is going to be, okay, we're going to have an alternator. And since when, okay, here I have an odd n, I get a negative. I'm just going to use negative 1 to the n. Then I have 2 raised to the, well, again, it was just whatever this number is, this n, so 2 to the n, over 2n factorial, right? Whatever this 6 is, that's what I have the factorial there, so I'll make this 2n factorial times A naught. All right, how do we make sure this works? Well, we're going to prove it by induction. So we do a proof by induction here. We'll check a base case first. When n is equal to 1, we would have A sub 2. Well, it would equal, what do we know A sub 2 is equal to? We can just go back up and see. A sub 2, it was equal to negative 2 over 2 factorial A naught. Well, what happens? Negative, okay, if you make n equal to 1, then you get a negative 2 to the 1 over 2 factorial A naught. Yay, that works, right? This formula actually works in the case where n is equal to 1. Okay, now comes the inductive step. Okay, so for the inductive step, we assume A sub 2n equals minus 1 to the n, 2 to the n over 2n factorial A naught. And we want to see what happens when we replace n by n plus 1. We want to prove that the formula still works in that case. So A2n plus 1, which is the same as A2n plus 2, is equal to, all right, well, we're going to use the actual formula. We have a recurrence relation. This is negative 2 over I copy this number, so 2n plus 2. I multiply by 1 less, so 2n plus 1. And then I multiply by a sub, well, I go down by 2, so it'd be a2n. But by our inductive hypothesis, a2n can be written in this form. So we'll do that. So we have negative 2 over 2n plus 2, 2n plus 1. And then here comes the a2n. It's an alternator, 2 to the n over 2n factorial a naught. All right, well, let's see. Let's put this all together. I have an alternator, but I have another negative sign. So this becomes an n plus 1 alternator. I have 2 to the n times 2. That's going to be 2 to the n plus 1. I have 2n factorial, but then I keep multiplying 2n plus 1, 2n plus 2. That's just 2n plus 2 factorial. Or, if you like, 2 times n plus 1 factorial, whatever. And then I have my a naught. And this is precisely what the formula would tell us to do. If I replace n by n plus 1, I should have an alternator to the n plus 1. I should have 2 to the n plus 1. I should have 2 times n plus 1 factorial, and then an a naught. So this proves it. Okay, so we found our even coefficients. Now let's do the odd coefficients. So we have the a1 as some just family variable, right? And then we go to a3. So this is going to be negative 2 over, we copy the 3, go down by 1 to a 2, and then we have an a1 because we have to go down by 2. All right, let's do a5. a5 is going to be negative 2 over 5 times 4 a sub 3. Now again, we can replace a3 with what we had up above. So I have negative 2 over 5 times 4 times negative 2 over 3 times 2a1. Now I want to put this together, and again, the negatives cancel. I get 2 squared, and now I have 5 times 4 times 3 times 2, and well, what's a times 1, right? This is 5 factorial, and then we have an a1. And immediately I see this is just playing out the same way as before, right? I'm not going to mess around with too many more terms at this point, right? So these are all odd coefficient indices. So in general now, I'm going to claim that a2n plus 1, right? I write it in this 2n plus 1 form to get an odd number, is going to be, okay, so let's see. This was 2 times 1 plus 1. This is 2 times 2 plus 1. Okay, when this n here, right, this 2, okay, is even, I get a positive. So yeah, same thing. I'm going to use minus 1 to the n. I'll have 2 to the nth power. I'll divide by, well, it looks like 2n plus 1 factorial, because it's the same number, right? If this is a 5, I get a 5 factorial. And then I have times a1. Okay, and I won't go through the detail this time, right? So, but the proof by induction is similar to the one below. Okay, and so we're able to now get the odd coefficients. Cool, right? The odd index coefficients, even index coefficients, that's everything. So now we can put this all together. So what does our y equal? Well, if we look at the, let's say we do the evens, right? Because we had those first. We would have minus 1 to the n, 2 to the n over 2n factorial x to the 2n. Okay, so we could put those together. N here is starting at, oh, and of course we forgot our a naught, which I can pull out. So I have an a naught, and here n would start at, say, 1. Okay, what about the odd coefficients? So there you have an a1, and we have a sum. We again have our alternator, 2 to the n over, and well, now it's 2n plus 1 factorial, x to the 2n plus 1, right? This ensures we're getting the odd ones. And again, our n can start at 1. Whoops, we're going to say start at 1. Okay, and so there we go. We have found our power series solution, for y. Now, a good question you might ask is, can we recognize these power series as regular elementary functions that we know? And with a little bit of cleverness, we actually can. So the observation that we're going to make is that, well, there's this thing that's popping up a little bit in here, namely that, well, we have this 2 to the n, and then say, for example, in this first one, we have x to the 2n. And I can write 2 to the n as the square root of 2 squared to the n, okay, or the square root of 2 to the 2n, and then times x to the 2n. And then I could bring these together as the square root of 2 times x to the 2n power. So if I do that, then I can rewrite this as, okay, a sum starting at 1 minus 1 to the n, and then I'm going to have 1 over 2n factorial root 2x to the 2n power. Okay, and we'll handle the other one separately. But if you just in your mind squint a little bit and just think of this as x to the 2n over 2n factorial with an alternator, this is a series that you actually know already, right? This is the sine series, right? Sine, the Maclaurin series for sine is x to the 2n over 2n factorial, stick an alternator, and then sum the series. Yeah, so actually this piece right here is just going to be a naught times the sine of, well, it's not x, it's root 2x, but that's okay. We just put a root 2x there. What about for this other one? Well, it's almost the same thing, except instead of x to the 2n, we have this x to the 2n plus 1. So in order to make these line up the same way, I would have to do something similar where maybe I'd say like, okay, root 2 squared to the n, and then I have one more of them, right? So I'm just going to toss another one in to make it a plus 1, and then I have to divide by it to compensate, times my x to the 2n plus 1. So I could put this together as 1 over root 2 times root 2x to the 2n plus 1. All right, so that's a little complication, but it doesn't really matter because this 1 over root 2, I can pull it outside the sum now. It's just a constant. And it's essentially going to get sucked into this a1 constant. All right, so if I do that, then I'm again just going to be left with, let's see, so I have this a1 over root 2, and then I have a sum starting at 1, my alternator 1 over 2n plus 1 factorial, root 2x to the 2n plus 1. And now, again, if you squint and just see this as an x to the 2n plus 1, you say, oh, this is just my cosine series. And so this bit here, that's cosine of root 2 times x. I didn't copy down this. It's a little bit weird because it doesn't look like it's the same thing anymore, but really, remember, you're going to be able, right, to put in any constants you like here. So dividing by root 2 doesn't change that fact. So at the very end of the day, we can conclude a general solution is, well, let me just change the letters altogether. Y equals some capital A times the sine of the square root of 2 times x plus some capital B times the cosine of the square root of 2 times x. And it turns out that this was actually the same differential equation as in problem 12, only we weren't given initial values in this case, whereas we were before. So before we were able to get specific values here. All right, but in any case, we can use the power series and a little bit of our powers of observation to get an actual general solution. Now, if you stopped up here, I wouldn't blame you, right? Like especially in the heat of a test, right? How are you supposed to see that that's actually, you can reduce these? Okay, but it's really good in practice when you have time to just peek around and say, okay, does this look like anything that we already know?